Hey guys, in this video we're going to talk about general equilibrium in our crash course. The only things that I'm going to focus on in this video is KP and KC. We'll do KSP in a separate video, so it won't be too terribly long. So let's go ahead and let's kind of start with our introduction here. So what we have when we're talking about equilibrium, we use those double arrows. And so you have the reaction going in the forward direction. You also have these reactions can go in the reverse direction. Well, whenever these rates going backwards and forth, remember we've talked about rate in the kinetics unit. Rate is all how fast or slow the reaction takes place. So when the rate of the forward and the reverse reaction are equal to one another, that is when you have equilibrium established. It's not when concentrations are equal or anything like that. It's where the rates of the forward and the reverse reaction are equal. So if we go back to kinetics and we look at those concentration versus time graphs, what we see here is this blue line is decreasing in concentration over time, and this red line is increasing in concentration over time. Well, what that tells us is that this is my reactant that's decreasing over time, and the red line is my product that's increasing over time. Now, there's a certain point in any reaction in which they no longer increase or decrease. Do you see how this red line is staying stagnant? This blue line is also staying stagnant. Right? They're not changing thereafter. That is the time in which equilibrium has been established. So whenever we kind of see that flat line of a graph, that's our equilibrium value. Now, I know I'm jumping ahead of myself, but when we're working with Rice charts, these initial values right there would go in the I line of my Rice chart. And these values here, these equilibrium values, are what we would see in the E line, the equilibrium portion of my Rice chart. So just a way that we could graphically represent these numbers. Now, what I have to the right here is if we have some stress in the equilibrium. So you see how all three of these are flatlined. All right, there's our reaction here. So N2 and H2 are our reactants, and NH3 right here is our products. Now, let's say we do something to change up the reaction. This is discussing like Shotley A kind of stuff. How does that affect these graphs that we see? Well, in this particular example, what we did is we added N2. So let's look at this reaction. Where N2 is here. And remember, according to Le Chatelier, and we're going to review this later on, if I add a gas that is in my reaction, then what I'm going to do is shift to the opposite side. So that means that consequently, I'm going to be making more NH3, and that's what you see here. I'm making more NH3, and then you're going to be using H2 in order to, as well as using N2 in order to make that stuff. So you see right here how that N2 is decreasing again. This H2 is also decreasing. And the reason why this is steeper than this one is because there's 3 H2s for every 1 N2. And so this system is going to change, increasing and decreasing over time until a new equilibrium is established. So this line right here, where you see them flatline once again, that's the new equilibrium that's established after we've applied a Le Chatelier concept where we stressed the system. Now again, what we did is we stressed the system by adding N2. When we added N2, we shifted the reaction to make more NH3, so that's why you see it increasing there. And whenever we're making more of my products, both of my reactants are being used, so they're decreasing in order to make those. So that's why you see a decrease here, as well as once you've added that, that's your spike, you see a decrease there as well. Okay, so this is a way that you can use Le Chatelier represented in these graphs as well. So these graphs can be represented to figure out where equilibrium is established, to fill out a Rice chart, or even to apply Le Chatelier's to see how the graph would be used. Now, the next thing I want to talk to you about is equilibrium expressions, okay? Now, when we write equilibrium expressions, we always want to write them for points, okay? So what we do is we take our products, you see C is a product here, raised to the coefficients over reactants raised to its coefficients. Now, if any of these guys in the reaction is a solid or a liquid, we do not include, sorry, let me pause. Sorry, I went an extra slide there. So we do not include solids or liquids in my expressions. So we have to pay attention to the states of matter that are written beside those as a little subscript. If there are any solids or liquids, we do not include them in there. Now, one other thing I want to talk about is the meaning of K. K just generically stands for equilibrium. Now, we've learned in this unit that we have several different brands of K. So we're going to talk about KC versus KP in just a minute, but this is just the general format of how you write those. Now, what K means, if you find a K value that is greater than 1, all right, so you calculate K is greater than 1, then that means that the products are favored. And that makes sense because these products values would be greater than these values in order for this number to be greater than 1. How that translates to thermo, how that translates to electrochem, remember we can start connecting all of these units now, is that it means that if the products are favored because K is greater than 1, then we have a reaction that is thermodynamically favorable, meaning that it happens on its own, and we give delta G a negative quantity for that. E cell values are positive. If K is less than 1, then the reactants are favored. And that makes sense because this value would be greater than the top. So that means this value, the K value, would be less than 1. And that means that the reaction does not proceed on its own. It's thermodynamically unfavorable, and we give it a positive delta G. Also, coming back to electrochem, E cell is negative in that case. Now, one other thing to remember is K is temperature dependent, okay? The only time when K changes is when temperature changes. So the next thing I want to talk about here is KC versus KP. We have to be very particular about the way we write KC versus KP expressions, okay? KC, we use molarities to plug in here. So because we use molarities, we use brackets in around whatever our products and reactants are. KP, you cannot do the same thing. Now, I know that some of you guys on your quiz did this incorrectly, okay? When I'm writing a KP expression, I cannot have brackets. Instead, I have to use parentheses, okay? And I've talked to AP readers, they are very picky about this. So you have to use parentheses. You also have to denote pressure because that's what KP is all about. It's about pressures. So what I plug in for KC is molarities. What I plug into KPs is atmospheres, ATMs, little pressures there. Okay, so I have to have the parentheses and the uppercase P to denote that I'm working with pressure there. But other than that, you write your KP and KC expression the exact same way. Now, if I calculate a KP value, that doesn't automatically mean that that's my KC value. Reason being, because pressure and molarity, they might have the same type of relationship, but they can't be used interchangeable. So if pressure and molarity can't be used interchangeably, then the KP and KC value can't be used interchangeably either. So we have an equation in order to convert between KP and KC. So this equation used to be on the equation sheet for older AP exams. It is no longer on the equation sheet. So you have to memorize this. And I call this the politically correct to change the nation equation. And I know most of you guys have already kind of memorized this equation. So politically correct to change the nation, let's show where I've gotten that from. So politically comes from KP, so this is the KP value. Correct comes from KC times RT. Now this R right here is your gas constant, 0.0821, and you're using this particular value because it doesn't deal with any energy. Remember, 8.31 is dealing with energy. This T right here stands for temperature in Kelvin. And then delta N is something very specific. A lot of people kind of mess this part up. So this is RT raised to the delta N. And what delta N stands for is the moles of product that's a gas minus the moles of gaseous reactant. So I take moles of product minus moles of reactant, but it has to be gases for both of those. Do note it is okay to have negative delta N quantities. That is okay. All right, so negative delta N quantities are okay. Just remember, do products minus reactants, and we only look at gases. And delta N is applied to R times T. I saw some people make that mistake when they were working on a quiz and some practice problems as well. All right, so that's how we convert between Kc and Kp. So in this next slide, what I want to talk to you about is manipulating K. So this is very similar to in thermochemistry, if you remember what we did with Hess's law of summation. However, the way we manipulated delta H values when we worked with goal equations is different from manipulating K values. The reason being is because the way you calculate K versus the way you calculate delta H. And if you have a question about that, you can come ask me directly. So when do I use this approach? So you use this approach when you have an equation with a K value. So that's what I gave you right here. And you have altered the equation in some way. So since you've altered this equation in some way, you can figure out a new K value of that. So here are the rules. If I reverse a reaction, I take the reciprocal. Reverse a reaction, I take the reciprocal of K. So it's 1 over K. If I multiply some number throughout a reaction, I take K raised to that number. And if I add multiple reactions, then I multiply those K values. So let me show you kind of what we're talking about here. So let's say that I have a new equation that is C yields A plus B. So what I do is I compare this new equation to the equation that I had previously. And I notice that this equation is reversed. Let me throw a little bit more in there. Let's say we have 2 in front of all of these. So not only has my equation been reversed, but it has also been multiplied by 2. You see, now I have those 2 coefficients there. So how can I manipulate this K value to figure out my new one? Well, what I'm going to do is, since I reversed it, I take 1 over my K value. And since I multiply my reaction by 2, I raise it to that power. So it'll be 1 over K squared would be my new K value. So my new K would be 1 over 2, and I square that value, which would equal to 1/4, or 1/4 translates to 0.25. So this would be my new K quantity for this reaction here. So if I reverse a reaction, 1 over K, if I multiply some number throughout a reaction, I raise K to that number. You can raise these to 1/2, you can raise them to 1/3, that's okay, all right? Now, if I had more than one reaction here, so let's say I took both of these reactions, and I wanted to add them together to make a new reaction, all right? So 1C would cancel out with this C, 1A would cancel out with this A, and 1B would cancel out with this B. So my reaction I would have is C goes to A plus B. So this is my newest reaction. Now, if I want to figure out how to find the new K for this, and instead of adding these K values to one another, what I'm going to do is multiply these K values and to figure out my new K value. So that's how we manipulate K. So now we're on to our discussion of Q versus K. You like my scribbles at the bottom? I didn't like the diagram that they gave you. I wanted to do something different in how I approach it. So that's why you see all the squibblies. Now, Q versus K. When do you use this approach? Well, you use it when you are trying to predict a shift to reach equilibrium. The reason why is because Q, which stands for reaction quotient, means that it's not at equilibrium. So what we have to do is use those initial values. Now going back to that rice chart, the I line, those are initial values. Those are what I plug in for Q. The way we write Q expressions are the exact same way that we write K expressions. It's just we use initial values instead of equilibrium values. K stands for equilibrium constant, meaning that it's at equilibrium. So we have to specifically use equilibrium values, which are the E line of the rice chart, when we plug in for K. Now, when we are using this approach, you will be given K. So you'll be given some value of K, and you will have to probably calculate Q and figure out which way the reaction needs to shift to reach equilibrium. So we're given K. Let's say that we calculate Q. Let's give a number to K. Let's say K is equal to 10. So we calculate Q, and when we do that, we find that Q is equal to 2. So what we do to compare Q versus K is we write both of them on the number line. Okay, and if we write them on the number line, then that helps tell us which way we need to shift to reach equilibrium. We're always trying to reach K. So if Q numerically is less than K, then we're going to shift to the right, to the product side, in order to reach equilibrium. Now let's say we had another example problem. And in that example problem, we found that Q was equal to 15. Now we put this on a number line compared to K. So K is equal to 10. Now remember, we're always trying to shift towards equilibrium. We're always trying to get to K. So if Q is greater than K, then that means that we're going to shift to the left in order to establish a new equilibrium, or to establish equilibrium in the first place. So we will shift to the left, we will shift to the reactant side in this case. Now, if Q and K are equal to each other, then you're already at equilibrium, so there will be no shift. So again, when we use this approach, we're trying to predict a shift to reach equilibrium. And so we have to determine if we're going to favor the products or favor the reactants to establish equilibrium, because we're not at equilibrium yet. In this next slide, I want to talk to you about your rice charts. Now, I know that some of you guys get a little disgusted whenever I say rice charts, but I promise you, if you know how to do rice charts effectively, it's going to organize your information to where it's so much easier to work out problems. So, when do we use a rice chart? When do we do it? Well, we use this approach to either A, find a K value, so we were trying to find K, or B, find equilibrium values, okay? So anytime we're trying to find either of those, then we are going to set up a rice chart. Now, if you know how to do this in your head, that's fine. It's just very easy to make mistakes. So that's why I agree, or not agree, crap, that's the wrong word, but I suggest for you guys to do rice charts. Now, when you're working with this, make sure you look for certain keywords. So initial, instant of mixing, introduced, those all go in the I line of your rice chart. Equilibrium values, when it says an equilibrium concentration, a pressure at equilibrium is blah, 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 those go in your E line. Okay, so make sure you fill in your charts appropriately. Also, don't forget stoichiometric relationships. So, for instance, I know that it doesn't pertain to this example, but if there was a 2 in front of this CO, then this would have to be minus 2x. If there was a 3 in front of this CO2, then this would be plus 3x. So make sure you apply the stoichiometry relationships down in this C line. That's very important. It will totally change your answer if you don't do that. Now, when you are working rice charts, you are given one of these pieces of information. A, you're given a K value. So if you're given a K value, you fill out your rice chart and you're plugging in all of these expressions into your K expression and solving for X. And once you solve for X, you can plug them in and solve for those equilibrium values. Part 2, if you are given one equilibrium value of any of these guys, then what you can do there is solve for X. And if I know what X is, I can figure out what all of these values are and then plug it into K to solve for it. Now, one other thing that you could be given is a percentage of something that's been converted. So they could say, okay, well, 20% of H2 has been converted to make CO2 and H2. Well, whenever you are giving a percentage, this is your code to help find X. So that is your code to help find X. So that is giving you some piece of information in order to find X. So X, in this case, would be 20% of 0.1. So make sure you know which one to apply whenever you're working with these rice charts. And if you have any questions or you want to rework some problems, you guys had the rice chart activity that you did, and you also have the rice example problems that you can go through if you need some extra help with these. So the last thing that I want to talk to you about in this little crash course for general equilibrium is Le Shotley A. Now, most of you guys are really good with Le Shotley A. Notice that you see here on the right-hand column of this little thing I picked up off the internet. So it says, which one of these things change K? This could be KP, this could be KC, it could be KSP, any of that, okay? The only things that change K is temperature. And we talked about at the very beginning during our introduction is that K is temperature dependent. And so that makes sense here. Now I scribbled out this effect on equilibrium because I didn't like the way they worded it. So I'm going to go through those with you specifically. Now, if we increase concentration, we're going to shift to the opposite side. So let me put an equation here. A plus B yields C plus D, something very generic. And so let's say we increase the concentration of A. Well, that is going to cause us to shift to the opposite side. So in this case, we will shift to favor the products. Now, when we're shifting towards the products, that means we're going to be making more of those. So these values will increase and these values will decrease. This is what we were talking about at the very beginning when we showed those graphs, how you'll see that little spike in the graph and then it'll start decreasing again. So make sure you know how to apply this Le Shotley to those graphs. If we decrease concentration, we just do the opposite. So if I had a decrease in C here, then I shift towards the decrease. So when we're increasing concentration, shift away. Decreasing concentration, we shift towards. Now you have to be very careful with this increasing, decreasing concentration stuff. If you are increasing or decreasing a solid or a liquid, there is no effect. So no effect if I'm changing a solid or a liquid. The reason why is because those solids and those liquids are not in my equilibrium expression, so therefore they are not going to affect my equilibrium. Now for the next one, we have an increase in pressure. When we are working with pressure, we can only look at gases. And we count the moles of gas that I have on my products and reactant side. So if I increase pressure, this can also be asked in terms of volume. So if I increase pressure or decrease volume, these work the same way, then I will shift to the side with the least moles of gas. Now make sure you're looking at gases only. It's the least side of gas. So let's say I have, these are all gases. So 2A plus B, which is a gas, and that is going to 2C, which is also a gas. So I have 2 plus 1, so 3 moles of gas on this side, and I have 2 moles of gas on this side. So if I increase pressure or decrease volume, because they go hand in hand, then I'm going to shift to the side where there's the least moles of gas, which in this case will be towards my products. If I decrease pressure, it just does the opposite. I'm going to shift to the side where the most moles of gas appear. And if I decrease pressure, how does that relate to volume? Volume and pressure are indirectly related. Okay? Let me skip down. I want to come back to increase and decrease temperature in just a minute. Add a catalyst. Now, when I add a catalyst, remember a catalyst lowers activation energy by providing an alternate pathway. You can probably spit that out in your sleep now. But what that means is that the reaction is just getting to equilibrium faster. Okay? It's just changing my rate. It's not changing equilibrium, so it's not going to cause a shift or anything. It's just going to make it happen faster. So adding a catalyst has no effect. Also, what I want to include in here is adding an inert gas also has no effect. All right, so an inert gas has no effect or no change as well. That's because they're non-reactive. They just take up a little space and that's it. Okay. Now, last but not least, let's come back to increase or decrease temperature. Now, the reason why I didn't like this little statement here is, I don't know, I just don't like it. I don't like to just memorize something. I like to make sense of it. So let's make sense of this. Now, we talked about, yes, temperature can affect my K. So let's talk about specifically what's happening. Now, when I'm talking about temperature, I first have to know, is it endo or is it exo? That's the first thing I look at. Remember, endo, positive delta H values. Exo, negative delta H values. Okay, so if I have an endothermic reaction, that means heat is going to be on my reactant side. So heat plus reactants go to products. This would be endo. If I have an exothermic reaction, my heat is going to be on my product side. So plus heat, we see this on my product side because this is an exothermic reaction. Well, now that we know whether or not the reaction is endo or exo, I apply that temperature change just like I do the concentration change to the heat. So if I increase temperature, boom, that increases. That increases for endothermic. If I were to decrease temperature, then that would decrease, my heat would decrease there. And then I shift according to the effect on equilibrium for concentrations. So if I increase heat, I shift away. If I increase heat, I shift away. If I were to decrease my temperature, decrease heat, then I would shift towards that decrease. Now, how does this shift right here affect my K value? Well, anytime you are shifting due to temperature and due to temperature only towards your products, that means K value will increase. Reason why? I'm making more products. Products is on the top, so therefore K will be bigger. If I ever shift to my reactants due to a temperature change only, then that means that my K value will decrease. Why is that, you say? Because reactants are on the bottom. If I make my bottom number in a fraction bigger, then my K value, what that number is equal to, will decrease. It will get smaller. So this is how we apply temperature change and how it affects your K value. So this is Le Shotley A. You have to be able to justify this, and for your response, make sure you say, according to Le Shotley A, make it sound all French and stuff. And then you justify accordingly. You're basically writing out this process in words. It's okay to do your sketches like this as well, but you have to explain it in words as well. So I hope this crash course was helpful. Don't forget to watch the KSP crash course as well.